I am Ankit Kumar Sahu, registration number 20BAI 1005, and this is a presentation which comes under the course of Theory of Computation. So, I will be talking about a hypercomputer, that is Zeno Machine, which is also called as accelerated Turing machine. What is hypercomputation? Hypercomputation refers to a model of computation that can provide outputs that are not Turing computable. For example, a machine that could solve the halting problem, that would be a hypercomputer. I'll be talking about Zeno Machine. Zeno Machine, abbreviated as ZM, which is also called as accelerated Turing machine, are a hypothetical computational model related to Turing machines that are capable of carrying out computations involving a countably infinite number of algorithmic steps. The idea of zero machine was first discussed by Hermann Weyl in 1927. The name refers to Zeno's paradox. Now, the formal definition of Zeno machine. A Zeno machine is Turing machine that can take an infinite number of steps and then continue to take more steps. This can be thought of as a super task where 2 raised to the power minus n units of time are taken to perform nth step. Thus, first step takes 0.5 units of time, and second takes 0.5, and the third takes 0.125, and so on, so that after 1 unit of time, a countably infinite number of steps will have been performed. Such a machine can run an infinite number of steps in 1 unit of time. Accelerated Turing machines have been discovered by Weyl in 1927 and studied by various authors. The following ATM can solve halting problem of the given Turing machine T and input W infinite time. Given program, write 0 on the first position of output tape, set 1 equals 0, begin loop, simulate the first I steps of T on W. If T of W has halted, then write 1 on the first position of the output tape, then 1 equals 1 plus 1, then end loop and end program. By inspecting the first position of output tape, we need 1 unit of time to run the above machine in order to decide whether T of W stops or not. Alternatively, we can log the computation and see whether the machine itself has halted before 1 unit of time or not. Are accelerated Turing machine physically possible? This challenging problem was discussed by various authors. Relativistic computation offers a physical model for acceleration. We contribute with a small result to this discussion by examining the computational space required by accelerated Turing machine running an infinite computation. The Turing machine executing the above set of instruction needs an infinite computational space. Set 1 equals 0, begin loop, 1 equals 1 plus 1, end loop. This is just an accident, or do we have a more general situation? The following Turing machine executes an infinite computation with only a finite amount of space. Set I equals 0. While I is greater than 0, do I equals 1, and while. A formal model of accelerated Turing machine is infinite time Turing machine, defined first in unpublished work by Jeffrey Kidder and expanded upon by Joel Hampkins and Andy Lewis. The infinite time Turing machine is an extension of classic Turing machine model to include transfinite time, that is, time beyond all finite time. A classical Turing machine has a status at step 0 in the start state and with an empty tape read head at cell 0, and then procedure for getting from one status to successive status. In this way, the status of Turing machine is defined for all steps corresponding to a natural number. An infinite time Turing machine maintains these properties but also defines the status of the machine at limit ordinals, uh, that is, ordinals that are neither zero nor successor of any ordinal. The status of Turing machine consists of three parts: the state, the location of read write head, the contents of tape. Just as a classical Turing machine that has a labeled start state, which is state at start of the program, an infinite time Turing machine has a labeled limit state, which is state for the machine at any limit ordinal. This is the case even if the machine has no other way to access this state. For example, no node transitions to it. The location of read write head is set to 0 for any limit step. Lastly, the state of the tape is determined by the limit supremum of previous tape states. For some machine T, a cell K, and a limit ordinal lambda, then this is the formula. That is, kth cell at time lambda is the limit supremum of same cell as the machine approaches lambda. This can be thought of as the limit if it converges or one otherwise. Accelerated Turing machine have been proposed as a model of computation more powerful than classical Turing machine based on their ability to solve halting problem. For classical Turing machine, Christian Claude and Ludwig Steiger present the following pseudocode algorithm as a solution to halting problem when run on Zeno Machine. Begin program, write 0 on the first position of output tape. Begin loop, simulate one successive step of given Turing machine on the given input. If Turing machine has halted, then write 1 on the first position of output tape and break out of the loop. End loop, end program. By inspecting the first position of output tape after 1 unit of time has elapsed, we can determine whether the given Turing machine halts. In contrast, Shager argues that the state of a Zeno machine is only defined on the interval from 0 to 1, and it is impossible to inspect the tape as time 1. Infinite time Turing machine, however, are capable of in implementing given algorithm. Zeno machines cannot solve their own halting problem.